Welcome back to Dave Does Math from Home. We are talking about 16.4. We're doing triple integrals. This is part 2 of this video series. So first one covered a lot of the basics and a lot of like the theory and the relationship between this and double integrals. I just want to do another example. So the the only example we have finished so far was a weird function that we integrated with constant bounds on everything. So it was the region we were integrating over was a box, which is a little boring, and the thing that we were integrating was a goofy function with trig and exponentials and polynomial pieces, and both of those things are a little unusual. Most of the integrals we're going to be doing in this section will just be integrals of dz, dy, dx. So there won't be like a function here. We're just going to be integrating one, but we're going to involve some really goofy bounds so that the functions get themselves involved. Full disclaimer, I haven't actually done this one yet. I just came up with it and I think it works out nicely, but we'll find out together. So if you're integrating the function 1, quick reminder that this represents volume, because dz, dy, dx already a volume. We don't have to have anything here for this whole thing to give us a volume. 1 is the easiest function to integrate. These are x's. X is 1. X goes to 0 from 1. Y goes from 0 to x. Z we have just integrated. The integral of 1 dz is z. We're evaluating that at 0 and e to the x squared. And our dy and our dx will hang out. So when we evaluate this, we still have x going from 0 to 1. We still have y going from 0 to x. And now we have e to the x squared minus 0. So just e to the x squared, dy dx. So that's not so bad. This is going to happen a lot where our first integral, if we're just integrating the function 1, our first integral is just going to turn into that letter, and then it's just going to sort of turn into these bounds. And it's pretty straightforward. So we need to integrate this with respect to y. There's no y's here, so the integral is going to be y e to the x squared, evaluated at 0, y equals 0, and y equals x dx. So I'll bring this up over here. We're going from 0 to 1 of x e to the x squared minus 0. So it's just this, which is good for us because until we had this x here, this was not integrable. This is an inside-outside other problem. We have a composite function. And in order to integrate it, we need to have this x on the outside. So the inside is x squared, the outside is e to the blob, the other is x dx. So we set w equal to x squared, dw is 2x dx. It's almost a perfect match. I just need a 2 here, which I can get by putting a 1/2 outside. Now the other and the dw match perfectly. And I can call this 1/2 the integral e to the w dw. This is still x going from 0 to 1. So this is 1/2 the integral of e to the w, obviously just e to the w, which is e to the x squared, evaluated at 0 and 1. So 1/2 e minus 1/2 of 1, or 1/2 e minus 1. And that's all there is to it in terms of the evaluation. Again, the evaluation bit of this is very, very similar to evaluating double integrals. What I want to talk about next is how to set up some of these triple integrals so that they represent things that we're interested in. So let me erase all this and we can start a new problem. Alright. I want to talk about the volume beneath z equals, or no, let's do it this way. Let's do the volume beneath 2x plus y plus z equals 6. This is a plane in the first octant. So, we are going to use triple integrals a lot to get volumes, much like we did with double integrals. First thing I want to do here is sort of create a picture and play with this a little bit. This is like the standard form of a plane, where you have all your variables on one side and your constant on the other. I kind of prefer it in more of like a slope-intercept thing. So z is 6 minus 2x minus y. This gives me a much clearer sense of what I'm looking at. If this is x and this is y and this is z, this tells me that I have a z-intercept at 6. The slope as I go along the y-axis is -1, so I'm going to hit the y-axis at 6 as well. My slope along the x-axis is -2, so I'm going to hit the x-axis at 3. And I have a plane that looks like this. So this is my picture. And I want the volume beneath this plane in the first octant, using a triple integral. So here's how we set up the triple integral. I know I want all three integrals, and I know I want 3 d's, and the order is something that I can play with a little bit. I generally like to sort of, one thing we talked about in double integrals is that once you do the inside integral, that dimension sort of collapses, and all you have left is just a bar, this interval on the last dimension. The same is true here. Once you do an integral, it's like you're sort of collapsing that dimension. So the first integral you do takes you from 3 space, it kind of collapses you down into 2 space, and now you just have your other 2 variables left. And then when you do the second integral, it collapses you down from 2 space into a one-dimensional bar, a line, a chunk, a line segment, I guess. And then you do that last integral over that line segment, and then you have your number, your quantity, no more variables anywhere. So, because of that, I generally prefer to sort of collapse the z dimension first, so that I'm just dealing with this on the xy plane. The xy plane, like I love playing around in 3 space, but I'm most comfortable on the xy plane, so that's typically my goal. So I'm going to do z first. And now I need bounds on z. If I'm in the first octant, my lower bound on z should be 0. Z can't go below 0 because that'll put me into a different octant. The upper bound on z this is where people are going to be real tempted to write 6. Because they're used to putting numbers here, and 6 is a very tempting number. It can't all be constants because then you would have a box. This is not a box. So we're going to have to put some of these functions in here for some of these bounds. It only goes up to z equals 6 along that axis. At anywhere else in this region, it's going up to a lot less than 6 because it stops as soon as it hits this plane, which is slanted downwards. Fortunately, we already know the equation of the plane solved for z. This is z equals 6 minus 2x minus y. This is the plane, that is the upper bound of all our z values. And once we finish this integral, the z-axis sort of collapses and now we're just on the xy plane. We can do y next. Integrating with respect to y is fine. So if we're integrating with respect to y, we're going sort of along the y-axis in this direction, which means that this is going to be the lower bound on our y values, and this slanted line will be the upper value. So y equals 0, the x-axis is our lower bound, and we need to figure out what this line is. And there's two ways you can think about this line. One way to think about this line is we know that it hits the y-axis at 6, and we know that it hits the x-axis at 3. So we have 2 points, we can find a slope, we can generate a line that way. We know the y-axis, we know the y-intercept. Probably, if it goes from 6 here to 3 here, the slope on the xy plane is probably -2 to go from 6. If it hits 0 after moving over 3 units, it must be going down 2 each of those units. So we have a slope of -2. We can kind of reason it out using these 2 points. Y equals -2x plus 6. That's our intercept, that's our slope, that's our line. We could use that here. The other way to get this line, if you don't like reasoning about what these points are, is this line is what our function looks like when z is 0. This line is on the xy plane. If it's on that plane, that means that z is 0. So 6 minus 2x minus y equals 0 should be the equation of that line. And if you add y to both sides, 6 minus 2x equals y gets you the exact same thing we had here. So, 2 ways to get the function for the middle bound. You can reason it out. You can, honestly, this is probably the safer way to do it, is just take the function that you know is sort of defining the boundaries of this and extract z from it and play with what's left. So y equals 6 minus 2x is my middle bound. And then on the x, if I do z and then y, the last thing I need to do is x. And after you have collapsed the z dimension and then collapsed the y dimension, all you have left is this bar of x-axis. And that goes from 0 to 3. No more functions involved whatsoever. Okay, we're 14 minutes into this video and we're ready to start evaluating this integral. The first step in evaluating this integral is really straightforward. The integral of 1 dz is z, just like in the last problem. So I'm going to set the x from 0 to 3. Y is still going to go from 0 to 6 minus 2x. The integral of 1 dz is just z, evaluated from 0 to 6 minus 2x minus y, dy dx. And then this is going to turn into x goes from 0 to 3, y goes from 0 to 6 minus 2x. Yeah, there we go. There's a nice x. So this is just going to turn into 6 minus 2x minus y. This evaluating the top, evaluating the bottom gets us 0. So we just have dy dx. And at this step, I want to pause. And I want to pause because I'm hoping that when I first put this problem on the board, I want the volume beneath this function in the first octave. I'm hoping that most of you were thinking I could do that with a double integral. I would integrate over x and y, and the thing that I would integrate is this function. That's what we just got. Secretly, this whole time, double integrals have just been the first step in triple integrals. If you want a volume, like the standard issue default way to do that is with a triple integral, integrating 1 in a triple integral. And if you're integrating 1, it's always going to turn into a z here, or whatever variable you're integrating first. It's always just going to turn into that variable, and then you're immediately going to replace it with these bounds, which, if you're going from 0 to z, it's the exact same thing as just integrating the double integral on x and y of that function. So that's convenient. From here, everything works exactly like the double integrals you've already known they work. There's shouldn't be any surprises here. There should be some weird math that's going to take 10 minutes to get through because fractions are going to get involved. But it shouldn't be a surprise because we have done stuff exactly like this before. It's just a double integral of a height function over an area to get a volume. But it started as a triple integral of 1 over this volume to get a volume. We're at 17 minutes, and I'm not sure I have enough time to finish this integral. I can try. I'll go through it really fast because it should mostly be review. Okay, so we're integrating with respect to y, which is going to give us 0 to 3. We want, what is it, 6y minus 2xy minus y squared over 2 from 0 to 6 minus 2x dx, which is the integral from 0 to 3 of 6 times 6 minus 2x minus 2x times 6 minus 2x minus 6 minus 2x squared over 2 dx. Because when you evaluate at 0, it's all just 0. So, from 0 to 3, 36 minus 12x minus 12x plus 4x squared minus 36 minus 24x plus 4x squared over 2 dx. So this 36 and this half of 36 will simplify into an 18. This is negative 12, and positive 12 leaves me with negative 12x. And this is positive 4x squared minus 2x squared is plus 2x squared from 0 dx. I haven't integrated this one yet. So now I can integrate this. We get the integral, no more integrals. We get 18x minus the 6x squared plus 2/3 x cubed from 0 to 3, which is 54 minus 54 plus 2/3 of 27 minus 0. So I get, these cancel, grand total, final answer should be 18. Just under 20 minutes, we nailed it, guys.